Thank you there's a lot more than the 3 people that said they'd be here yesterday. I only have strip waffles for 25, so I'll put them out here at the end. Making a subset difference, so hopefully you came here because you thought that sounded intriguing and you didn't think that crypto meant cryptocurrency. This is all about cryptography here. I'm going to start off with a disclaimer. This is based on my understanding of the AACS specification. I've never had to fully implement this. I don't work for those kind of companies. I've not even seen code for an implementation of it. I'm sure it's under NDAs and stuff like that. I'm presenting this because I didn't find information when I was trying to look at this stuff. So essentially this was something I thought was interesting. I was looking into anti-piracy measures. And there was no kind of material telling me what the hell a subset difference was and what does it do, why is it useful, how does it work. If you see errors in these slides, if you see errors in how I've interpreted things, or if you know better because you've done this kind of stuff before, let me know. You can either shout it out and everyone knows here, or let me know. I'll update slides and post corrections everywhere. Don't worry about it. What am I going to be covering? Because I didn't really go into that much in the kind of the description. So a brief description of what AACS is. So if you're not aware what AACS is, I'll be going into an explanation of the subset difference tree. So that's the kind of meat of this subject. What that is. How this kind of tree structure in the key system allows you to revoke users and stop people being able to access media, and how it enables efficient revocation of non-contiguous sets. So saying that you don't have to be within this particular contiguous set, you can have this person revoked and this person, but everyone in between them is allowed to still access that media. At the end, I'll be sharing a link to a reference code base that I've been working on because I find it's really easy to learn this kind of stuff by actually coding it, testing it out, finding out that it works the way I think it should work. There's a whole bunch of things that I found out by implementing it that I didn't realize. And if I talk really fast, then I've also got some slides at the end that might help you if you start to look into the specification. A couple of gotchas, one thing that I think is wrong in the specification, just some useful hints and tips, essentially. What is AACS? So the Advanced Access Content System. It's basically the new thing after we had CSS for DVDs. So if you're one of those people that, like me, who has DVDs at home and you've ripped all of them onto a hard drive because, you know, DVD decryptor is a thing, this is the new and improved version that was brought out to stop people ripping all the Blu-ray discs, and that's why you don't find Blu-ray disc rips online, but you do. Anti-piracy methods, and it's also on HD DVDs if you even care about those things that don't exist. It's a collaboration of a number of the big players. Basically, they all got together, formed this AACL licensing authority, and said, this is how we're going to encrypt stuff from now on. So what are the aims of it? So for this, it's designed for mainly disk media. And so it's to protect the media from being accessed by unlicensed devices. So you've got to have a device that has a specific license, and they've got a key that they have obtained from the licensing authority that allows you to decrypt that media. If they find that a manufacturer, say Sony, has implemented it wrong, and you as an end user have now got access to copy that media, they want to be able to revoke that drive so that from then on that drive can never decrypt any media in the future, thus, you know, preventing more Blu-rays being ripped in the future. A really important statement here really is that it's the revocation of stateless receivers. So what we mean by that is these receivers do not necessarily have an update function. In fact, you should assume that they don't have an update function because that will get around some strategies about people that just refuse to update things. Look, for example, at the PS3 where we had the Linux kernel vulnerability where you used to be able to run a Linux subsystem on it, and then they kind of patched that out, but there's a whole bunch of PS3s that still have the old version because people kept it and stopped patching it so they could keep these old versions of PS3s. It should not significantly impact disk space. So when we're looking at digital disk media, space is a premium. If I can have an extra 100 megabytes, that's more quality I can put into the content. Maybe I can put into some additional, some additional scenes or some cutscenes or something like that. So we really want it to take up minimal space on the disk while still providing that great security that we need. And it should be coalition resistant, so if I pwn 2 machines, then that doesn't necessarily give me access to anything else. And no matter how many machines I pwn, if I revoke all of those pwned machines, then I still can't, even with the sum of all that secret material, somehow access the media. So, revocation of stateless receivers, it gets mentioned in the specification, and it's mainly based off of this paper, the revocation and tracing schemes for stateless receivers. So, this paper goes into how this gets implemented. It goes into a previous version of it, or the kind of academics behind the original, but AACS then takes a slightly different approach and how it implements it, and it's kind of like a more updated version. But the basic assumption is we don't assume that anything can be updated remotely, so we don't have the non-patch strategies. But a con of this is that we can't revoke access retroactively. So if you know anything about DVD or Blu-ray disc decrypting, you'll know that when a new revocation list when a new revocation list comes out, then you can no longer decrypt anything from then on, but you can still decrypt any disks released before that new revocation came about. Because there's no way of them actually actively stopping you getting a disk that was 2 years old and a device that was 2 years old, and that still works. So yeah, a device can still decrypt any media from before it was revoked, but the idea is that from now on you can't get the next blockbuster film that comes out on Blu-ray disc, or you can't get the next cool media that comes out. So, quick little 3-point rundown on how the actual media is encrypted. It's AAS CVC'd. So you just have a giant CVC of the entire media, or splits of media. Each piece of media is a title. All of the title keys are then encrypted with what's known as a media key. And then to get a media key, you go through the subset difference system. So realistically, you need to retrieve one key, which then decrypts a whole bunch of keys, which then gives you your stream keys. But this is the key we really care about usually. And the media key can be derived, a device can derive a media key by looking at its set of device keys that it was given when it was manufactured, and it can, if it's not revoked, get that device, figure out that media key, enables it to decrypt the title keys, enables it to decrypt the media. Right, the meat of this presentation. What is a subset difference tree? What does it do? How does it work? Why is it great? It's really quite interesting. I'm going to start off, if you know anything about kind of video decrypting and stuff, you'll recognize the forum Doom9. And this is probably the only piece of informative blog forum post you will find about AES. It's the only one I could find. And he was trying to describe, or they were trying to describe, how subset systems work, and they use the analogy of a truck. So if you imagine each device is a truck with a trailer, inside that trailer is a whole bunch of crates which are protected with keys of some sort. You're on a very weird system, but you cannot reverse and you cannot take corners of greater than 90 degrees, right? So these rules will be in the corner when I show you this image, which hopefully makes this make a bit more sense. So here we've got a truck down here, and this truck can go up there. It can make this corner because it's 90 degrees. It can make this corner because it's 90 degrees, make that one, but it can't get to there. It can't get to there. It could go all the way here, can't get to there. Can get to there because that's less than 90, there. You can kind of see how it gets to certain places, but there's certain places it can't get to. And so you could imagine that if we have crates, if we supply crates to this, and the keys for it are in these car parking spaces, that truck cannot access any of the crates. But if it can get to, if we've got 2 crates that are in there, but 1 crate that's in there, it can drive around, open that 1 crate, it's got its media key. So, just for even more clarity on that, the truck is your device, the crates are the encrypted media key data entries. They are on the disk alongside the media. The codes at the car parking locations are what's called processing keys. The prize inside the crate is obviously a media key. And every junction there, I'm just going to term it as a node. So it's a point in which we can make a decision on where we go next, and we have a piece of information, we can derive further information. It's important to note that you don't ever actually go up the tree. That's just for the use of this analogy. You only go down from certain spots. So I guess you could say that, so here's a kind of junction A, junction B, we could say those are nodes. That's the junction A's processing key. And instead of going up, we think with portals, we just portal up to a certain location that we could have gone down, and we start navigating down from it. Let's already get into the crypto on that. So what do I mean by that? Well, each node's key is derived from a higher key in the tree. Right, so when we had a node, you can figure out any of its subnodes, any node that comes down from it, because basically you hash it 3 times and you get left, processing key, and right. So if you have that key, you can get to the left, right, and the processing key. If you have one of those keys, you can get to any keys below it, and that kind of funnels down. And that allows you to get any key that's not on, any key that you've got a parent of, you can get to. How are we going to use this? Well, when you are giving a device, you assign it somewhere on the tree, and the bottom level of the tree is what are known as device node numbers. And each device is one place there. As a device, you get every key that is one different from your path to the root of the tree. Now that sounds really crazy, and you probably don't know what that means. It's really hard to visualize. Don't worry, I'm going to explain it. Say we've got this lovely looking tree here, and these will be device node numbers, and there's a tree going upwards. If I'm this device down here, I'm not allowed to know any of this information, because if I could get this, I could derive mine. If I could get this, I can derive mine. I can never derive my processing key. If I get one that's one different, that means I can get this one. I get the one over on the left there, and I get this one on the right here. And those are the only 3 device keys I get in this system. But from that, I can obviously derive the lower keys. And you can see that I can get to any key here that's not in purple. And hopefully that makes sense to you, and how I'm taking the original nodes. As a device, I get given these, and I can derive any of the lighter green ones here. So what does that mean for revocation in this system? Well, revocation is fairly easy. We essentially just encrypt that media key with something that your device cannot access. So something along your path, essentially. So if we go back to this diagram here, it's helpfully already labeled that P here that's in red is any place that that truck cannot get to. So if that truck is to be revoked, we just encrypt the media key with one of those entries. That truck can never get to it. But hopefully you can see that if the truck was here, and we use this one, and it was here, it could get to it. Every other truck can get to that location, and so on. So, but let's say I wanted to revoke these 2. Well, I can encrypt it with that key, because neither of these 2 trucks could get there, but every other truck can. If I want to revoke these 2 as well, in this contiguous set here, I'm just going to move that up. And thus, I can encrypt there, and hopefully you can see that none of those trucks could ever get to that car parking space. But again, this whole side of it could get up there if they wanted to, and they can retrieve that key. Now, the problem arises when we enter a non-contiguous set. So what if we want to revoke here? There is no car parking space here that those 5 can get to, those 5 can't get to, that these 3 could still get to. Essentially, if we were revoked here somewhere, then all of these are revoked. So this is where the subset difference system actually comes into its own, and that's where the more interesting part lies. So it's a bit like ogres, which are like onions. So it has lots of layers, and in order to do that non-contiguous revocation, we have loads of layers. So specification written here, quite wordy. Essentially what it is, for every level that we have within our master tree, let's call it, if you go 1 level down, there are 2 separate trees at that level on top of the existing tree. So we have say we have a 3-level master tree. At level 1 down, there is 2 extra level 2 trees. At a 3rd level down from that, there are 4 extra trees that are not as tall. You take 1 level away each time, essentially. And what you say is that you can't go higher than the original tree. Again, this all sounds very wordy, and so this is why this material is going to be available as slides, and there's going to be code, and I'm going to keep explaining it. But how does this help? So when we've got multiple trees, what we end up doing actually is that we can do 1 encryption per tree, and that revokes all of those items underneath that encryption. But then in the lower tree, we can re-enable certain sections by having a tree that only certain people can access, and we encrypt in there, and then only bits of that get revoked. And we kind of re-enable, revoke until we go down the tree and get the exact subsets that we want. And so hopefully this will be a bit more obvious if I display it visually. So imagine this is our grand master tree, and right now everyone's unable to access any media. And then I want to revoke anything under here. So I've done a revocation at this level, and anyone in this triangle can no longer access this media. But then in a lower tree, somewhere down here, and again, this is a different tree layer, so there'll be a big tree here and a smaller tree, I re-enable this set, and then I might also revoke this set down here. So as you can see, I've now, these users can get it, these users, and those users on the end. I've disabled discontiguous sets here. And when we do that, we have to define the path down to this kind of subtree here. And we can actually move that across and say that this consists of two subsets of users. So we have the subset rooted at level 0, so the root tree at level 0, with a revocation at a depth of 2 along a certain path, let's say somewhere down here. And then we move over and we re-enable a subset rooted at level 4, so 4 down the original and along this certain path of the original, and then we can revoke again at a depth of 1 within that tree. Again, I realize this might be confusing. Hopefully it'll make a bit more sense. Now, I just want to quickly say some naming conventions. Generally, left we give it a 0 path, 1 we give it right we give it 1, and so we never really care about the absolute root node. You're never going to give that out to anyone because they could drive the whole tree. But we give you 0, 0, 0, 0, 0, 0, essentially. And that's how we kind of denote where different places on the tree are. Hopefully this will give you some examples, and that might help you understand things. This is something that's definitely missing from most media that I was finding some examples of how this might work. So let's say we want to revoke, and here I've laid out, a 3-depth system. So the top level root, we've got a 3-deep tree. Below that, we've got two deep trees, and below that, we've got 4 1-deep trees essentially. So this is the entire system. And let's say I want to revoke 0, 0, 0 over there. And the easiest way of doing that is to encrypt in the tree A, encrypt with the 0, 0, 0 key. And hopefully you can realize that all of these devices would be able to get to that in our parking system, and that is the only device that cannot get to that location. Okay, so that's a simple one. We could already do that. What if we wanted to write 0, 0, 0, 0, 1? We've already seen how we do this. This is simple layer, 1-layer revocations, contiguous sets. If we go to a discontiguous set, so we've got the 0, 0, 0 and the 0, 1, 1, what are we going to do? So we revoke with the highest level, the highest common factor in the highest tree. So in this case, 0 is the common ancestor, so we revoke with that. So hopefully you realize that these can all access that, but none of these can, right? But we still want these two to be able to access the media, and at the moment they're revoked. So we're also, on the lowest level, we're going to encrypt with these two. And again, 0, 0, 0 cannot access that, and it cannot access that. It also cannot access any of these because you can see these are separate trees at this point. Also, you can hopefully see that these unrevoked systems can still access the keys that they can access some key within the media key entry. So we end up with 3 different encryptions in the media key data entry system, and each device that's not revoked will be able to find one entry that it can decrypt, thus getting the title keys, thus being able to access the media. And just another one for good luck. You can see here that we can actually revoke these two here, and with that we have efficiently revoked only the ones that we needed, and we've only done it in two encryptions, but we've revoked 3 different systems at this point. So if you're like me and you want to see the code for all of this, I've been working on some implementations of it. I originally started it off in C because I like writing AES encryption in C. I've done it too many times. But I also wrote an implementation in JavaScript, and that's the one that actually runs fully because I didn't bother implementing AES. You can run an example of it. I also include the examples in these slides, so you can run code for them and see which bits can be encrypted, decrypted. You can run through the bit streams that happen. You can see when revocations are occurring. And I'll stop quickly and ask if there's any queries now, or we can go on to like the 3 slides of bonus material because I've got 4 minutes. So, yep.
Just a quick one. How much do these revocation lists get used?
What do you mean?
In the real world, like, are they actually effective in stopping pirates?
Okay, so a revocation list, how does it get used? So what happens is, I forget the version number of MKB we're on, so you get an MKB version on Blu-ray disc media. And so every so often, the licensing agency releases the latest MKB that they're going to use, which includes the latest set of revocations. Right? From then on, anything that they've revoked can no longer access media of Blu-ray discs that are being created. That prevents piracy in those regards. It kind of prevents forward piracy in that regards until you crack into another device. Now, it's up to the device manufacturers to store these secret material in a way that should not be reverse engineered. We've already seen cracks of it. There's a reason why you can crack Blu-ray discs online. And I'm not going to get into this presentation. I have another presentation when I talk about piracy and anti-piracy. This was kind of like to provide some technical stuff behind it about how pirates are keeping their secret and how the licensing agency is attempting to revoke as many as it can. So hopefully that answers your question. Yep.
How big is the tree?
How big is a tree? I actually have that in the bonus questions. Bonus material. Boom. So we actually have a 32-bit system. In a later bonus slide, I'll show you that there's 1 bit of that is not used, so there's actually only 31 possible, 31 tree depth. So there's 31 trees, 31 layers, sorry. A device gets n amount of keys from a tree depth of n. We have more trees for every layer. So there's 31 layers, they get n from each. You end up with 496 different device keys. Each device key is just a AES encryption key, so it's only 16 bytes. It's about 8 kilobytes of data to put on the device as secret material. And so that's an important thing here. We're really limiting the space here. The device only has to have 8 kilobytes of secret material stored. And on the actual disk, you're looking at, so a common MKB record might only be 64 bytes long, something like that. It's like you need the encrypted key and a bit of information, an encrypted key and a bit of information, so 32, 64 bytes. Well, you get longer as you do more revocations, obviously. Every encryption takes about 22 bytes in an MKB record. But as you can see, we can, like, huge swathes of things can be revoked in one encryption. Cool. Any other questions? I'll just quickly run through the slides before you cheer. Cheer and shout. If you're reading the specification, this is how nodes are defined. We define them with a UMask and a VMask. UMask defines which tree down it's in, so the absolute root master tree at level 0 has a UMask of absolutely 0. The whole thing is valid. And then, as you can see, this one would be 3 deep and on a path of 100 compared to master tree. Hopefully that makes a bit of sense. VMask says that how far up in the node it is. So anything below it we don't care about. So this node is there, and then this is just extra space. Confusing storage, how do we store these kind of things? We add a bit on the end just to signify where the end of the path is. So if you're ever reading the specification, there's a difference between a device number and a device node number. Hopefully this slide explains that for you if you need to. And either I'm wrong or the specification is wrong. This function does not do what it says it does. So I added an extra check in my code. But the maths doesn't quite work out, I think, how they expected it to there. Basically there's an edge case here that was annoying me, and I thought that I completely misunderstood the specification about 2 days ago before this presentation. I was like, shit. Right. And that is everything. Hopefully you've enjoyed the talk, learned something about cryptography. The GitHub's already up there. The slides I haven't put up anywhere yet, but I will put them up. They'll be available on my GitHub and wherever else needs to be posted. Thank you.